All right, this problem's a little more complicated, and one thing I often do is draw a picture on a problem like this. So if we remember that the central limit theorem tells us that the distribution of sample means, if we take all the sample means and plot them in a distribution, we know that they'll be normal. So we can go ahead and draw that. We also know something about the mean of that distribution, and that is that it's going to equal the mean of the population distribution. So this is, in this case, 140. Right, and then we want to know basically what's the probability that the sample mean will differ from the population mean by more than 1.8 millimeters. So this is our population mean. How spread out are these sample means? Well, here's where we do have a correction factor. So the standard deviation of sample means is equal to the population standard deviation divided by square root of the sample size. And if we had the variance of the sample means would be equal to the variance over the sample size, but we're just going ahead and taking the square root of both sides there. So in this case, we have the standard deviation is 8 millimeters there, and we have the square root of the sample size. So the sample size is 49. Square root of 49 is going to give us 7. And so this is going to equal roughly 1.14. So that tells us the standard deviation of this particular distribution of the sample means of size 49. And we want to know how many of these are off from the population mean by more than 1.8 millimeters. So if I draw this in here and we say that this distance is 1.8 millimeters, we want all the sample means right here, what portion of the sample means are there or are over here. Now you can't really tell in my kind of ugly drawing here, but one thing we do know is this is symmetric. So we know that this portion right here is equal to this portion. So if we could find either one of them, we could just double it to get our answer. Our answer is what portion of the distribution here is in the shaded regions. So since the tables work out much nicer on the left side of things, these standard normal tables, let's focus on this one right here. How could we figure out what portion is right here? Well, we know that if we get a z-score, the table will give us the portion to the left of that z-score. The question is, what is that z-score there? In general, our z-score has been this right here when we have a normal distribution, but we really do have a normal distribution here because the central limit theorem tells us that the sample means follow a normal distribution. So let's go ahead and use this formula here, and let me just remind us that for the standard deviation of this distribution, we're using what we calculated before, the distribution of sample means standard deviation. Okay, so this here, basically we're 1.8 off of the mean, off of the population mean. So instead of knowing these values directly, we know that that difference is 1.8. This is how far off is our value from the population mean, and we already know that we're 1.8 below the population mean. And this one here would be a z-score. This top value would be a positive 1.8 if we did want to calculate it, which we're not going to need to. And then we're going to divide that by that 1.14 that we already came up with. And if we type this in, so we're looking at negative 1.8 divided by 1.14, we get roughly negative 1.58 when we round that. So that's our z-score value. That's this z-score value here, and we can look that up on the table. So we're going to the standard normal. We're going to the negative infinity to negative z because we're on the left side. Positive z would be over here. And we are looking for that z-score of negative 1.58 right there. So that's 0.0571. That's the portion that's in this one tail right here. But we know it's symmetric. We know that we have to double that. So we're going to take 0.0571 times 2. And that will give us 0.1142, which will be our correct answer there. That's the total portion of the sample means that would be more than 1.8 millimeters away from that population mean there.